Okay, so everybody, so let's continue our class. So I developed a comprehensive MATLAB code for moving pendulum as a model of your leg, and we derived the marginal label unstable system, and based on the roots that we were gonna call poles after this in this class eventually. And I uploaded the MATLAB file to Canvas and send it to you by emails, right? All you received. So now let's continue. In the previous class, I told you that if you have such a differential equation and you apply the input of the impulse and I introduce impulse d, there is no solution for this because delta of d is an unknown function, right? Please mute your speaker, please, all of you. Guys, please mute. Okay, so delta of t is, I told you, at time 0 is unknown. At time is not 0, is 0. So you cannot find the differential equation with the right hand of unknown. So that's why, and plus preliminarily I taught you the block diagram, right? Based on the moving pendulum problem. So that you have the controller, you have the open loop transfer function G that I'm going to introduce one by one after Laplace transform. Then you have a sensor here, obviously, H, the output of the system and the input of the system. But this block diagram, even though I'm going to show you in MATLAB and Simulink mainly is in the S domain, frequency domain. Okay. And I told you in the beginning of the class, we are transferring everything from time domain to frequency domain, S domain, that is J omega or I omega. Okay. So that's why today I'm going to introduce, for those of you that you are not exposed to Laplace transform, to Laplace transform. So if y is equal to a function of time, so Laplace transform of that function is f of s, because we are transferring to time to s. So, and the Laplace of that function, f of t, classically is being defined integration from 0 to infinity e minus st f of t dt. Guys, how many of you already had ME430? How many of you already had? None? Okay. So this is Laplace transform. This is the definition of the Laplace transform. Exponential minus st, s is our Laplace variable, ft dt. Saying that, I told you that we have many inputs to the system. One of the inputs, number A, is y is equal to delta of t, impulse. And I introduce impulse means a huge amount of force or torque or a heat source in a very short period of time. Here we go. That was the impulse that I introduced in the previous class. So here is 0. Please mute your microphone, guys. Please mute your microphone. I'm saying speaker. Okay. So having that, so I now want to know what's the Laplace transform of. I'm just developing this for example, but I'm going to skip a few of them because I'm wasting your time. What is the Laplace transform of impulse? E minus st dt, because your f of t is impulse. Can I go to the next page? Yes? Everyone? Good. So, but as I taught you, impulse is unknown function. So that's why I manipulate delta of t a little more. How? I'm gonna just open this area, just magnify this area. I want to see what's inside. Okay, I manipulate that. I say these are the zeros. This is the zero. Now I'm saying, okay, let's assume that the impulse is this rectangular. Okay, this rectangular. That happens, as I told you, impulse, look at this. See, in a very short amount of time. I'm saying delta tau, a short amount of time. So delta tau is much smaller than 1. Very short amount of time. And I told you impulse has a very huge value. So this is a huge value, guys. Here we go. So I can say huge value is this 1 over delta tau. Because if this is epsilon, short amount of time, 1 over epsilon is a huge amount of value. Much greater than 1. Okay? So, being said, so Laplace of f of t can be written because before 0 is 0, after 0 is 0. Only is valid for this. So I'm saying from 0 minus epsilon to plus epsilon, okay, very short amount of time. Delta of t, e minus st dt. So we are talking about the zeros. See what I'm saying? So I'm putting time t0. If I put time t0, here is 1. Because we are talking about the upper bound, lower bound, 0 almost. So what you're going to get is this. Minus plus delta of t dt. Guys, from high school, when I say integration, what do I mean? Integration of a function. If it's the function given t and f of t and has area. So the area under this delta t. What's the area of this rectangle? How much is that? Area of this rectangle. Yep, 1. Here we go. So the Laplace of impulse is 1 always. Clear? You don't need to know the process. I'm just teaching you just the beginning of the Laplace transform. So you just have to, because just Google it. There's no Google, okay? B, if your input to the system is unit step, so the Laplace of this 0 to infinity, this is unit step, means this, remember? T unit step. This is unit step. There we go. Here is 1. E minus SD dt. If you do that, because this is 1 at the end of the day. So we're going to be from 0 to infinity. This is simple. I'm just doing that to show you. And this is from high school is 1 over s e minus st from 0 to infinity. If you put the upper and lower bounds, bingo, 1 over s. You see that we are changing time domain to s domain, to frequency domain. Clear? Guys, I cannot see what you are chatting with me. You have to talk. Okay? So, oh, can I go to the next page? Yep. Oh, okay. Go ahead. Let me know when you're done. Yes, go ahead. Yeah, this is how scientifically we are showing the step function, unit step function. We are showing with this sign, okay? It's similar to one, but it's not one. See what I'm saying? Resembling, yeah, is resembling one value, okay? This is, okay. So, C, if the input to the system is ramp, here we go. From high school, we have seen this a million times. Y, T. A straight line, here is 45 degree. Is ramp. The name of this is ramp. Ramp. So the Laplace of y of t is integration from 0 to infinity t e minus st dt. Do you know how to solve this differential equation? I'm so sorry, this integration? Do you know? Yes, by parts. This is u dv is equal to uv minus v du. This is part by parts integration. I'm just skipping that because this is ridiculous. It's wasting your time. So it's going to be 1 over s squared. Here we go. Please do it as homework for yourself at home. And get this if you want. But you don't need to. You have to eventually memorize it. And or Google it in. Google it to find it. C, D. If your function is parabolic, or input to the system is parabolic, you're gonna tell me, oh Payman, how you can visualize a parabolic input to the system. It's very easy, guys. When you trying to make a race with your friend in a car, you are pushing the gas pedal eventually like this. Right? So this is to speed up. This is parabolic. That's the input to the system, guys. Control-wise. Okay? So Laplace of that again, part by part integration. I'm skipping that because we have lots of things to do. Is 1 over s cubed. So the take-home message is that, guys, t to the power of 1 Laplace is s squared. T to the power of 2 Laplace is s cubed. So now I can make a general statement. If this is t to the power of n can be any number from 1 to, I don't know, 100, whatever. So the Laplace of that is n factorial divided by s n plus 1. This is polynomial to the power of n, Pn. So you can validate this. Validate parabolic. How? Parabolic, based on this formula, is 1 over 2, 2 squared. So the n is 2. Gonna be 1 over 2, n is n 2 factorial, divided by s 2 plus 1, 3. 2 factorial, but 2 goes to New York. The answer is the same. Here we go. Clear? Yes? So, Can I go? Let me know when I can go ahead. F. If the input to the system is this minus AT, what's the name of this in mathematics or engineering? You are graduating, guys. If you don't know, that's a shame. What's the name of this in mathematics, this function? Don't tell me I don't know. If you tell me, I'm going to hit my head to the wall. Come on. Please, this is high school, man. T, I do know, but technical name. At T0, it's 1. At T infinity is 0. I'm just plotting that. You tell me in English, what do you see? The profile of the function. Yes, decaying term. Here we go. If the input to the system, and they're gonna tell me, are you stupid, payment? How we can have decaying term? Eventually, you're gonna see that we're gonna model a second order system with the first order based on a decaying term and this kind of interesting things. Okay. So it's easy peasy. So Laplace of y of t is integration from 0 to infinity e minus st. Your function e is minus at dt. The proof of this is very simple. So because it's e minus s plus a t dt. If you put the upper bound and lower bound and do the integration, it's going to be s plus a. So if here is, this is take a message. If here is minus, let me change the color. If here is minus, here is plus. If here is plus, this is going to be minus. Inverse sign. On the other hand, if I give you y is equal to e for t, its Laplace of y gonna be 1 over s minus 4. See? Inverse. G. Here we go. If you have a given function of f of t, and knowing that its Laplace transform is f of s, as we introduced here. Here we go. Okay. Now I want to see what's the Laplace transform of t minus t naught. What's the name of this behavior in the engineering? Yes, the guys that they have the ME430 with me, they know that, huh? Delay. Because it's gonna happen if this is say f, when I see ft minus t naught, it's gonna happen exactly t naught. Here is delay. It's happening. So having that, a Laplace of ft minus t naught gonna be e minus s t naught f of s. They have the same sign, guys. Minus, minus. If here it is plus, you're gonna be, oh, we don't have plus because it's gonna be causal system. I'm stupid. Okay. This is delay. And in delay, we are modeling the second order system with first order system to design PID controller based on the Nichols-Ziegler that I'm going to teach you eventually in this course at the end of the semester. Can I go ahead? Yeah. In negative. Oh, they have the same sign. They have the same sign. Okay. These have inverse, but here has the same sign. Okay. So give me an example. So suppose your t is ramp or parabolic. Now I'm saying that calculate Laplace of yt minus 3. If I visualize this in engineering, this is this. So it's a 1, 2, 3. When I say this has delay, means it starts from here. Here we go. See what I'm saying? Yes? So, based on whatever I taught you, because your T naught is 3, so it's going to be E minus 3S f of original function. But the original function we just calculated. Where? Here. Here we go. So it's going to be E minus S3S or S cubed. Here we go. We found the delayed parabolic. See what I'm saying? Yes? Good. What was G, F, G, H? I forgot the alphabet. So, if your input to the system is harmonic, we name this harmonic. The guys that you've passed vibration course with me, ME520, you know that we name this harmonic, not periodic. Okay, sine omega t. So if your system, and we name this frequency response in the control and the vibration. Your input to the system is harmonic. So the Laplace transform of this going to be from 0 to infinity E minus SD sine omega t dt. How to solve this integration again, guys? How to do that? Part by part. Yeah, part by part. I'm not doing that because it's stupid. Just wasting your time. Gonna be omega divided by s squared plus omega squared. We name this excitation frequency in the control and the vibration. This is excitation frequency. Excitation. I hope that you passed vibration before coming to this class. Yes? You didn't have? Okay. You have to have. Because the course names indicating that the sequence of the course. ME520. This is ME530. See what I'm saying? Okay. So this is excitation frequency. Like assume that some of your friends shake your hand harmonically. Back and forth, back and forth, back and forth. It's exciting your body by a frequency. See what I'm saying? Or suppose the car is on a road with a harmonic. This is the tire of your car and the suspension system, spring. We're going to talk about this in the control. And damper, it's going to move on this, on the road. So the road has what? excitation frequency. So now if I tell you, can I go to the next page? Huh? Example of this, if I say y of t is sine 5t, find the Laplace of sine 5 t minus 10. Bingo. So first of all, what is this I told you? Look at here, guys. What is this? Delay. So this is your T naught. So you're gonna have E minus your T naught is 10. 10s f of s, original function. Now we know that based on whatever I taught you, the original of the y, original Laplace transform of this is omega, excitation frequency 5, divided by s squared plus omega squared, 25. So the delayed sign input of the system gonna be E minus 10s multiplied by 5 s squared plus 25. Here we go. Clear? Yes? Great. So H L. If y is cosine omega t, another harmonic term, but has a phase shift of 90 degrees with the sign, so its Laplace of y, again, gonna be 0 to infinity, e minus st cosine omega t dt. And if you do the part by part, I'm just sticking that way. I'm not stupid to develop that here. Gonna be s squared plus omega squared. Only difference with the sign is this. Sign has omega, here it has s. Clear? Now if I say calculate Laplace of sine 2t minus 1, I mean cosine. Cosine. You see that your system is undergoes the delay. There we go, and this is your T naught. So the Laplace of that, obviously, gonna be E minus S, because T naught is 1. Here we go. F of S. Based on whatever I taught you here, F of cosine gonna be S. S squared, your frequency is 2, plus 4 in this E minus S. Here we go. Clear, everybody? Yes? Okay. Can I go ahead? Yes? Okay. So, M, if your function is given as f of t, and its Laplace is f of s, and now if I ask you calculate E add the function with the decaying term, multiply by the decaying term. So the answer gonna be simply f s plus a. You see, it's changing the sign. So if here is minus, here is minus. If here is plus, here gonna be minus. Example. Say your y is cosine of 3t. Now I'm asking you to calculate Laplace of e minus 5t plus 5t cosine 3t. So first you have to calculate Laplace of the original function. Based on whatever I taught, is going to be s squared plus 9. Excitation frequency square. So it's going to be, whenever you see s, you're going to replace with s minus a, because this is positive. See? Positive, s minus a. So you're going to be s minus 5 here, divided by s minus 5 square plus 9. Bingo. You are multiplying decaying term or not that, or exponential term. So because positive is exponential. Okay. Or if I say another one, if I say y is equal to sine 2t, and I ask you calculate e minus 10t sine 2t, based on whatever I taught, the Laplace of the sine is 2 s squared plus 4. So this is gonna be, whenever you see s just is minus, you have to use plus 1, s plus. So it's gonna be 2 divided by s plus 10, because your a is 10, square plus 4. Bingo. Clear, everybody? Yes? So, may I move? May I go ahead? Yes, I can. And if you have a given function as input to the system, not input, f of t, now I want to calculate f prime of t, the first time derivative of t, means df over dt. I'm going to do this as an example, but when I go ahead for the differentiation, I'm going to skip the proof. So Laplace of that is integration of 0 to infinity f prime of t instead of f e minus sd dt. Now I'm going to use part by part. How? I'm going to say e minus sd dt is d is d. Oh, sorry guys, I made a mistake here because I'm teaching from my mind. F prime of t dt is dv, and I'm saying e minus st is u. So this is gonna be equals to uv, as I told you in the previous pages, v du. Okay, great. We have u already. By integration from the both sides from high school, you know that v from here gonna be f of t. Because integration of derivative is function itself. Now you can replace it here. u is e minus st, and the v is f of t. But you have the bounds from 0 to infinity. Minus, again, from 0 to infinity, v f of t in du. So du from here is simple. Du is minus s e minus st. So putting here minus s e minus st dt. For God's sake, this minus with this minus multiplied, this becomes positive. And also for God's sake, again, this s is not variable divided with time, comes out s. Now let me know what is this. Go to the page 1 of today's lecture. What is this, guys? Go to the page 1. There we go. What is that? What is that? Yes, this is the definition of Laplace. This is f of s. So I can replay here. Now I'm putting the upper bound, lower bound here. E minus s infinity f of infinity minus e minus s0 f of 0 plus s in f of s. This is 0 because s to the power of minus infinity is 0. This is 1. So simply like that, this is a general statement for the first time derivative of Laplace is s f of s minus initial value of that function at time 0. This is general statement. Clear? Example. Can I go ahead? Can I? Okay. Example is this. If your function is sine 40, I want to see what's the Laplace of sine 40 derivative. Based on what I said is s f of s and f at time 0. F at time 0, if you put time 0 t0, how much is this? 0. Because sine of 0 is 0. This is 0. Now you have to calculate f of s. Based on whatever I taught you previously, sine of 40 gonna be 4 divided by s squared plus 16. You have it now. I'm just putting here, gonna be 4s divided by s squared plus 16. And you can validate that. Why? Because time derivative of this is how much from high school? Come on, you let me know. This is high school. What's the time derivative of this? 4 cosine 40. Yes? So now Laplace of this, which is this obviously, Laplace of this is 4 cosine is s squared plus 16. Bingo. We got it. Clear, guys? Yes? P. If your function is f of t, now what's the Laplace of f double prime, second time derivative of that? Again, using two-step part by part that I'm skipping from here. Okay, I'll give you the answer. Is s squared f of s minus s f at 0 minus f prime at 0. I'm sorry. Okay. Example of this. Can I go ahead? Yes? Good. If I say your y is e minus 2t, I want to say what's the Laplace of e minus 2t second time derivative. Based on what I taught you previously, the Laplace of this, if you look at here, here we go. Minus 2t is 1 over s plus 2. See here? You have it in your notes. So, it's going to be Laplace of this, f of s, originally, is 1s plus 2. But from second time derivative is s squared f of s minus s function at time 0 and its first time derivative at time 0. So at time 0, how much is this? 1. So this is 1. There we go. Now f prime, y prime or f prime from high school is minus 2e minus 2t. At time 0 is how much? Minus 2. So your answer is this. S squared in f of s, s plus 2, minus s, minus in minus 2, plus 2. There we go. This is the Laplace of second time derivative of this decaying term. Clear, everyone? Now I give you this example and 5 minutes to give me the answer. If y is e minus 3t sine 3t, find the Laplace transform of this function. 5 minutes. Do that and let me know the answer. Anyone? So first we have to calculate the f of s of this. F of s of this function is, remember that was this, when you multiply by this term, gonna be fs plus a. Remember that I taught you. So the original of the sign was 3 in s squared plus 9. When you're multiplying by this decaying term, you have to replace s with s plus 3 squared. This is the original function of this Laplace. Or writing like this, s plus 3 squared plus 9. Now we want to have the second term. It's going to be s squared f of s. So 3 divided by s plus 3 squared plus 9 minus s f at 0. Look at here. S f at 0. At 0, this is 0. That's 0. So this is 0 minus f prime at 0. We have to calculate that. So y prime or f prime gonna be minus 3 e minus 3t sine 3t, first and second, plus second and first. 3 cosine 3t e minus 3t. This is f prime. At where? At time 0. At time 0, this is 0. This is 1. This is 1. Gonna be 3. So you have a 3 here. Bingo. Clear, everybody? Yes? So because I told you, let me find it. I told you if you have a function f of s for f of t, if you multiply by this term, e minus at, the Laplace of the whole term is going to be fs plus a. Remember that we had this example? Yes? So now, this is the same. Laplace transform of sine is 3ds, but multiplied by this decaying term. So instead of s, I'm going to put s plus 3. That's right. This is original Laplace of the whole this term. This. Now I have to put here s squared. Oh, I excluded these guys. Let me write 3s squared s plus 3 squared plus 9 minus 3. So s squared, here we go, f of s, bingo, at f of 0 is 0, then we have the time derivative, putting 0, it gives you 3. Understand? Everybody? Yes? So you saw that, where we are. Oh yeah. You saw that first time derivative showed s here. 1s. Now you saw that second time derivative gives you 2s. S squared. That's right. So I'm going to stop it here because next class I'm going to talk about this derivative integration, okay? That how we generate general formula for the derivation, and then integration, and then we're gonna move to block diagram. Okay, guys. Thank you, guys.